So hi everyone. Today I'm going to explain a little bit about how can we identify if we are operating in a CCM or DCM operation. So I'm going to explain some of our typical converters that we explained so far, such as the buck boost and the buck boost, and you can also apply the same logic to the other converters in order to find whether you're operating in the DCM or the BCM or in the DCM operation. So let's look at, so this is DCM basically and BCM. Okay, so let's look at some of our converters. So a buck was basically, we had a switch and a diode here, and then we had an inductor. For a boost we had an inductor, then a switch here, then a diode. For buck boost we had a switch here, then an inductor and a diode here. And for flyback which is essentially the same as the buck boost. So if we had the polarities as negative, so we would have something like this. Okay, and so let's look at, so if this is IL and this is ID, so I'm gonna do the same for O. So ID, this is IN, this is IN here, then ID here. Okay, now let's draw some graphs. So let's draw the graph waveform. Oh shoot. These guys. Okay, and so if this is IL and this is ID, IL, ID, IL, ID, IL, ID, and bring this here, bring this here, and bring this here. Okay, so now, so our IL here, so let's say if we are operating in BCM, it starts from 0, it goes up here and then goes down, and then our ID would be 0 when the switch is conducting and would be equal to IL when the switch is off. So same thing here, So this goes up and then this goes down and then switches on, the diode is 0 and then switches off. Here the direction of this IL here is like this, IL, then so ID would be like this, and so here we have ILM here. If this is a 1 over n ratio, so if we have this, we would have current, but not the same as IL. It has a transformer ratio conversion between these two. Okay, so okay, how can we identify if we are operating in the DCM or BCM mode? So one way to look at this is that, so one approach that I want to take is that as long as between, so if this is time DTS, the duty cycle multiplied by the TS, DTS, and then this is TS, DTS, and then this is TS, DTS, TS. So when do we go into DCM? So when this the current in the diode reaches 0 before we actually hit the end of our period. So as long as the diode current remains positive between DTS and then TS, then we're operating in the CCM mode. If not, so if it reaches 0, that means at another point it will further on it will go into negative, and then which it will go into reverse bias, and we will go into DCM mode. So we can write this as, so one way to identify the boundary is by evaluating these figures, right? So as I explained, so the converter is in CCM slash BCM, yeah. If the diode current is positive, not 0, for DTS, T between DTS to TS. Because if it reaches 0, then we would go into the DCM mode, right? So when is our actual here diode here positive? So when IL is also positive, right? So the diode current is positive when IL is positive, or to write it mathematically, so IL, which is the average of the inductor current, has to be greater than, let me write this in the middle part, I think it's an important equation. So IL has to be greater than delta IL divided by 2, where IL is the average of ILT, and delta IL is the peak-to-peak. Current ripple of IL of t. Right, so as long as the average here is greater than the basically the peak-to-peak ripple divided by 2, we're operating in CCM because IL always remains in positive. Okay, thus the condition for operating in continuous and discontinuous modes are so IL greater than delta IL divided by 2 for CCM, and then IL less than delta IL divided by 2 for the DC. Where I and delta IL are found assuming that the converter operates in CCM. So for example, let's do this for buck converter, right? So if you recall, the average of the inductor current in buck converter ILTS was equal to IR. That was only in buck converter, right? So which is equal to V out divided by R, and V out is equal to, because we are assuming that the converter operates in CCM, so this is dV in divided by R, and if it's not, we'll see that this equation will happen. So we won't have this equation, so therefore we will conclude that we have to be operating in DCM. So now I found IL. Now delta IL, if you recall from before, can be found from V out times D prime LFS. So now putting this into the CCM equation, IL and delta IL, I have also, I should have mentioned that this was for buck. Okay. So IL is greater than delta IL divided by 2. Therefore, ILD V in divided by R from here is greater than delta I L V out D prime L Fs, right? And then here we can write this again from dV in divided by R greater than V out is also dV in, so we didn't need to actually convert this into dV in because V out would have cancelled with V out here, divided by LFS. Therefore LFS divided by R is greater than D prime. So this is the condition for CCM when operating in buck converter. So if we have this condition, we're operating in CCM. This expression can be expressed as okay. K greater than K critical, which is a function of D for CCM, and if K is less than K critical of D is for DCM. Where K is equal to, oh shoot, so I forgot to add the 2 here, 2 LFS, yeah, okay, so K is equal to 2 LFS divided by R, and then my K critical for buck converter. The function of D is equal to D prime or 1 minus D. Right, so if my K critical, which is the D prime, is less than K, which is 2 LFS divided by R, then I'm operating in CCM. If not, I'm operating in DCM. This is for buck converter. So if we were to draw this, actually, let me draw it with this. Oops. Okay. So, and let's say that okay, so this is equal to K, and this is my K equal to 2 LFS divided by R. So I have my K here, and then if this is a function of D, I would have my K critical being a line like this, right? Where this is the K critical of D equals D prime. So if I'm operating So my K is 2LFS divided by R. It's not dependent on the duty cycle. That's why it's a constant value. So if my duty cycle is below this point here, so that means that D prime is greater than, that means my K critical of D is greater than my K. So K critical of D is greater than the K, so I'm operating in DCM here. And if I'm operating here, that means that my K critical of D is less than K, right? Which means that I'm operating in CCM. So this is how you basically determine whether you're operating in DCM or CCM operation. One of the ways you can determine, but it all stems from this equation here. There's nothing more to it really. So you just plug in whatever values you have for your average inductor or your peak-to-peak ripple current of your inductor current, and then you'll end up with this equation that you had here as K and K critical. Why did we do it as K and K critical here? Because this can be expanded to also other converters that use the same K but different K criticals. So if you look at other converters, so a similar mode boundary analysis can be applied there as well. A similar mode boundary analysis can be performed for other converters. The table below shows the CCM slash, not slash, CCM or DCM mode boundaries for buck boost and buck boost. Okay, so converter buck boost. I'm not gonna do the analysis of how we're going to drive the K critical in the boost and the buck boost. I'll leave that to you guys, but I'm gonna give you what you should end up with. Critical of D, then what is the max of this value? So for buck, we said that it's 1 minus D, the K critical of D. For the boost, it will come out to be 1 minus D to the power of 2. And then for the buck boost, it will end up being 1 minus D, which is the D prime. Oh, sorry, 1 minus D, not 1 minus D prime, to the power of 2. So the maximum here is 1, this is 4 divided by 27, then the maximum here is 1. If you want to find the buck boost for, the boundary condition for the flyback, it's very similar to the buck boost, except that it is divided by the turns ratio n squared. Okay, so the same thing that we said over for the buck applies here too. So in each case, K remains the same, which is 2 LFS divided by R. So the only thing that changes in this equation here is the K critical, and then the K remains the same for determining whether you are operating in the CCM or DCM. And basically the mode boundary is given by maybe again. K critical of D CCM, and then K less than K critical of D for DCM. Okay, so that's it for how to determine if you're operating in the DCM or CCM mode.